Good evening, everyone. My name is Rohan Jadhav, and this is the live session and sample problem discussion for polymer reaction engineering. Here we will be discussing some sample problems so that it will help you solve this week's assignment. Starting from the first question we have for an isothermal liquid phase second order reaction, P given Q. Uh, in a PFR, the ratio of time required for 80% conversion to time required for 45% conversion for this reaction is. So in this question, it is asked that for a second order reaction which is occurring inside a PFR, what is the ratio of the time at these two conversion levels? So starting from the performance equation of a PFR, we have uh, tau, that is your time, equivalent to Ca naught. Ca naught and an integral from 0 to xa, that is the conversion, and inside the integral term we have dxa by minus r. So here, as you can see, Ra is your rate term. Here we can observe that this is a second order reaction. So we will be adding the rate equation for a second order reaction uh, in this place, and then we'll be equating this uh, with respect to the conversion which is occurring inside. So the conversion term, this expression will be integrated with respect to the conversion term going from 0 to xa, and the value of xa will change, will be integrated for 80% and 45%. So with respect to that, we will have two times that will be at 80% conversion and then another time at 45% conversion. So when you take the ratio of this, you will be able to calculate what is the time required, what is the ratio of the time required in these two cases. Upon solving this, you will see that the ratio of the time required will be around 4.88. So that is how much time it would take for 80% conversion to occur when compared to the 45% conversion to occur. Moving on to the next question. If in the above question, leading from the first question, if the PFR is replaced with three CSTRs of the same volume, then the exit conversion of the reactant is. Now we know that in a CSTR, the concentration decreases rapidly as soon as the reactant enters the CSTR reactor. So we are replacing an entire uh, PFR with three CSTRs in series. So in this case, what we need to do is we need to again equate the same equation for the second order reaction, but for a CSTR. So the performance equation of CSTR will be like this. Again, in the RA section, you will have to add the second order reaction kinetic expression for uh, the liquid phase second order reaction, and then we have to again calculate this with respect to the conversion factor of this reactor. And the exit conversion for this can be calculated by this formula, which is defined for CSTRs in series, where uh, you can see that tau is the time and k is the rate constant for the reaction. And for three CSTRs, this would be the expression for calculating the exit conversion of reactant A at the exit of the third CSTR. And when comparison is made with the PFR, uh, we will see that the exit conversion will be around 0.926 when we calculate through these expressions. Moving on to the next question, we have for equilibrium considerations in closed systems. the relationship in between the degree of polymerization Xn and equilibrium constant K can be expressed as. So equilibrium constant determines the degree of polymerization very crucially, as if the equilibrium position is reached, equilibrium state is reached in a reaction, what would happen is the reaction would not proceed either further or backwards, as the degree of the polymerization process itself halts at that position. So because of that, the expression which defines the uh, dependence of equilibrium constant with degree of polymerization, starting from a monomer giving rise to extending change of a polymer. We can say that the first expression, that is the degree of polymerization, is equal to 1 plus k power zero point 0.5. So that would be affecting the degree of polymerization in this way. Uh, as the equilibrium constant, root over equilibrium constant is determining the, it's very sensitive to the degree of polymerization, as I've explained right here, that once the equilibrium constant is reached, the degree of the polymerization process would halt, and the degree of polymerization or the ripples present in the longest chain would be controlled with respect to that. Moving on to the next question we have. Which of the following statement is false for the importance of solvents in polymerization process? In the presence of a strongly protic solvent such as DMSO, higher molecular weight polymer can be obtained. So this statement is true, as DMSO is able to dissolve high molecular weight polymers. It is it can easily give rise to higher molecular weight polymers during reactions. Since it's a highly protic solvent, it can make the functional groups more accessible, because of which high molecular weight polymers can be obtained. It helps in accessibility of functional groups with a reduction in the viscosity of the reaction mass. Since viscosity of the reaction mass is getting dissolved in the strong solvent, it is easy it is easier for monomers to reach the functional groups, because of which the higher molecular weight polymer can be formed more easily. Third, we have, it influences the rate of polymerization and molecular weight due to preferential solvation or relationship with either the reactant or the transition state of the reaction. Yes, so since solvents are able to dissolve the polymers more easily, what would happen is that preferential solvent of the polymer itself will make the entire area of the reaction more accessible, and its relationship with either the reactants or the transition state of the reaction will possibly give rise to higher molecular weight polymer. So, in case of finding out the false statement for solvents and polymerization process, none of the above is the option you have to go with. Next, we have the kinetics of the polymerization process is important for to understanding how is the reaction proceeding over time, reaction mechanism, and rate of polymerization. This is a pretty straightforward question, which is asking you to define how kinetics and the polymerization process are limited and what kinetics for a polymerization describes. So kinetics describes the rate of a polymerization process. So when rate is when rate is brought into the picture, we time also matters a lot. So because of this, the polymerization reaction proceeding over time is understood by the kinetics of the polymerization process. Next, we have the reaction mechanism. Reaction mechanisms can be defined as reactions in series, different reactions occurring in series, or reactions occurring in parallel. Since these scenarios show us that formation of undesired or desired products, or formation of intermediates and the final products, how these reaction mechanisms arise is also understood very well by kinetics of the polymerization process. Since favorable and favorable reactions are a commonplace, it is necessary to understand the kinetics so that uh, we can improve on the rate of the favorable product process so that more pure polymer product is formed. Next, we have rate of polymerization, which is quite synonymous to the kinetics of the polymerization process. So we can see that all these three uh, parameters describe the kinetics of the polymerization process. Next, we have the step growth polymerization process. Reaction begins rapidly, but higher molecular weight is obtained slowly at the end of the process. Step growth polymerization process at its initial stages does occur rapidly. As the monomer comes in contact with any kind of initiator, it will join together with other monomeric species to give rise to the polymer at a rapid rate. But as time goes on for the reaction, higher molecular weight chains are only formed at the end of the reaction when the reaction is reaching the equilibrium. Reaction is reaching the equilibrium where the shift in the equilibrium will stop, and that is the position where the highest molecular weight polymer will be obtained. So this statement is moving on to the next question. Polycondensation can be carried out with the help of various polymerization techniques such as solution, solid state, and emulsion polymerization. This is also a very straightforward question, which shows that condensation polymerization, as shown in an example right here, we can see that we have two monomer groups, and when they are combining, they shed out the water molecule, giving rise to the polymeric species. Now, this condensation reaction can be formed in all of these polymer reaction processes, as you have studied in your previous lectures, that solution, solid state, and immersion polymerization are pretty capable of performing the polycondensation process through these processes. Excuse me. The average molecular weight obtained in step growth polymerization is limited by rate of reaction, equilibrium, or rate of diffusion. For the average molecular weight, which is seen in step growth polymerization, rate of reaction would not affect it much, as the reaction rate will only describe if the process is taking place slower or faster. That has little concern over how average molecular weight of the product is obtained. Whereas reaction equilibrium plays an important role, because since the equilibrium shift is the place where the reaction would stop occurring, and as the reaction is nearing the end, it starts forming its highest molecular weight polymer, polymers. So that's why average molecular weight is drastically dependent upon the reaction equilibrium. Then rate of diffusion as such does not have much role to play in uh, determining the average molecular weight obtained through step growth polymerization. So the correct answer would be reaction equilibrium. The viscosity of the reaction solution increases significantly with increase in conversion. So the removal of byproduct molecules from the viscous mass becomes first option. We have a process of rate control. Second, we have important to obtain higher molecular weight and pure polymer product. And next, we have not an important process. So if we analyze this statement, we have viscosity of the reaction solution increases significantly with increase in conversion. So this is a true statement, since as the reaction goes on, monomeric species will combine together to form long chain polymers, and as long chain polymers are formed, the viscosity of the reaction solution will increase continuously with time. You draw a graph with time, and the viscosity, if you see, it will increase with time as the reaction proceeds, because large scale entanglements will start occurring in the newly formed polymer, and that will result in increase in viscosity. So the removal of byproduct molecules from the viscous mass becomes a process of rate control. So if we have competing reactions, Uh, if we have competing reactions and we have a byproduct, for example C, and the main product is the polymer P, we can see that the removal of the byproduct molecules from the viscous mass, which is being formed, becomes a process of rate control. How rate control? Because you're eliminating uh, the byproduct and increasing the purity and the selectivity of the main polymer molecule. Because of which the process rate control becomes a crucial step uh, due to the removal of byproduct molecules. Next, we have important to obtain higher molecular weight and pure polymer product. As I defined just now, that if the byproduct is removed, more favorable reaction will proceed towards the main polymer reaction process, and because of that, there is a good chance that the molecular weight of the polymer will increase as favorability is shifted towards the other side, and because the byproduct is removed, pure polymer product will be obtained. So both A and B describe accurately how the removal of byproduct molecules from the viscous mass will result in uh, the reaction solution significantly increasing in conversion. Moving on to the last question we have. The application of interfacial polymerization is useful in manufacturing of reverse osmosis, encapsulation of inks, and insecticides and medicines. So in reverse osmosis process, we have a membrane which selectively separates out solutes and solvents in response to osmotic pressure. So here we are concerned with formation of an interface where the uh, polymeric membrane will be responsible for separating of the solute or solvent bodies. And that's why reverse osmosis is a field where the interfacial polymerization has high application. Next, we have encapsulation of inks. Now, encapsulation of ink, what happens in encapsulation of ink is that if ink is floating in a medium where it is filled, what happens is encapsulating the ink in a polymeric coat. What would that result in is that it will form an interface between the outer medium and the ink itself. And because of this, the ink will get encapsulated and it will settle down at the bottom. So that's why encapsulation of ink is uh, is a good application for the interfacial polymerization process. Next, we have insecticides and medicines. Insecticides, the use of insecticides on plants or other bodies, what it does is that it forms an interface on the surface of the material, because of which it starts protecting it from any kind of outer body harm, out, outer environment harm, because of which it functions very well as insecticides and medicines. So, because of that, uh, all the options right here are excellent examples for the application of interfacial polymerization. So the correct answer here would be all of the above. So I would like to thank you for attending this session, and I hope that you'll be able to finish your uh, assignments quickly this week, and we will see you in the next live session. Thank you.